Imagine a race where participants must run through a maze. The fastest ones emerge first, while the slower ones trail behind. Gas chromatography operates on a similar principle, but in this case, the racers are different components of a mixture, and the maze is a column filled with a stationary phase. Gas chromatography is a common type of chromatography used in analytical chemistry for separating and analyzing compounds that can be vaporized without decomposition. It plays a crucial role in testing the purity of substances, separating components of a mixture, and identifying compounds. In essence, gas chromatography is the science of separating the invisible. Gas chromatography may sound complex, but it's composed of a few key parts. Picture it as a race with each component playing a unique role in the journey from start to finish. Firstly, we have the gas supply, acting as the carrier. This is our wind, pushing our competitors, or in this case, the molecules, onwards. The type of gas used often varies, but helium is a popular choice due to its inert nature. Next up is the injector. Think of this as the starting point of our race. It's here that the sample is introduced and vaporized, ready to compete in the race. Then comes the column. This acts as the racetrack. It's a long coiled tube where the real action happens. The molecules race along this track, separating based on their different properties. Some are quick, some are slow, but each finds its own pace. Now, at the end of this race, we have the detector, our finish line. It identifies and measures each molecule as it crosses the finish line, determining the order in which they arrived and the time it took for them to get there. Finally, we have the data recording system, our scoreboard. This system records and displays the data collected by the detector, allowing us to analyze the results. Each component plays a vital role, working together to separate, identify, and measure the mixture's individual components. There are several types of gas chromatography, each with its own strengths and specialized uses. The two main types that we'll be focusing on are gas-liquid chromatography, or GLC, and gas-solid chromatography, also known as GSC. In GLC, the stationary phase is a high boiling point liquid. This method is often used for the separation and analysis of volatile organic compounds. The high boiling point liquid can effectively absorb and separate these compounds, giving us precise results. On the other hand, in gas-solid chromatography, the stationary phase is a solid. This type of chromatography is particularly useful when dealing with gases and small polar molecules. The solid phase can selectively adsorb these molecules, providing us with detailed insights into the composition of the sample. So whether you're using GLC or GSC, the choice ultimately depends on the nature of the samples being analyzed. It's all about finding the right tool for the job. Like any method, gas chromatography has its strengths and limitations. Knowing these can help us maximize its advantages and mitigate its weaknesses. Let's start with the strengths. Gas chromatography, or GC for short, is highly regarded for its high resolution. This means it can separate compounds that are very similar in structure, making it incredibly precise. It's like being able to tell apart identical twins just by looking at their fingerprints. Next, we have sensitivity. GC is capable of detecting even the smallest amounts of a substance, down to parts per billion. Imagine being able to find a single grain of sand in an Olympic-sized swimming pool. That's how sensitive GC is. And let's not forget speed. With gas chromatography, results can be obtained rapidly, often within minutes. This makes it particularly valuable in time-sensitive situations, like drug testing in sports or environmental monitoring. However, gas chromatography is not without its limitations. One major drawback is its inability to handle large, non-volatile or thermally unstable samples. Essentially, if a compound can't be vaporized without decomposing, or if it's too large to travel through the GC column, then it's a no-go for GC. This limits the range of compounds that can be analyzed. Another limitation is the need for skilled operators. While GC machines are becoming more user-friendly, interpreting the results still requires a certain level of expertise. This can be a barrier in settings where such expertise is not readily available. And lastly, like any instrument, GC equipment can be costly to purchase and maintain. This could be a deterrent for smaller institutions or developing countries. Understanding these strengths and limitations not only helps us use gas chromatography more effectively, but also drives us to continually improve and innovate in the field of analytical chemistry. As we continue to push the boundaries of what's possible with GC, we can look forward to even greater precision, sensitivity, and speed in the years to come. So, there you have it, a quick guide to the fascinating world of gas chromatography. We've explored that it's a method used to separate and analyze compounds with its own unique components. We've uncovered the different types, each with their own special applications. And of course, we've discussed its strengths and limitations, showcasing the importance of this tool in scientific research. Next time you encounter the term gas chromatography, you'll know that it's not just a fancy term, but a powerful tool in the world of science. Thank you for tuning in.